In this next section, we'll practice finding explicit formulas for geometric sequences. Given the geometric sequence with a sub 1 equals 3 and a sub 4 is equal to 24, find an explicit formula for the sequence, then use it to find the sixth term in the sequence. So we already talked about the recursive definition of a geometric sequence where you're told a sub 1 and then a sub n is equal to the one that came before it times r, the common ratio. Explicitly, we can define geometric sequences this way, that the nth term is equal to the first term times r to the n minus 1. So we can use this explicit formula to do this problem. So we know that a sub n is equal to a sub 1 r to the n minus 1. And so in this case, n is equal to 4. So the fourth term, 24, is equal to the first term, 3, times r, which we don't know, to the n minus 1, r cubed. And so we really just have to solve this formula for r. Dividing both sides by 3, we have 8 is equal to r cubed, and so we can see that r is equal to 2. So a sub 1 would be 3, multiplying by 2, we get 6, multiplying by 2, we get 12, and that gives us our fourth term of 24. Now we were asked to find a sub 6, so we can just keep going since we're so close. The fifth term would be 48, and the sixth term would be 96. If we weren't close, we could use this formula, because now we know explicitly the sequence can be written a sub n is equal to the first term, 3, times the common ratio, 2, to the n minus 1. And so this formula would allow us to find any term in the sequence we were interested in. Let's try another example. A sub 1 is equal to 2, and a sub 3 is equal to 50. Find a sub 5. I think this one would not, well, I guess we can do this one. All right, I was going to say it's not very interesting because these are so close together, but I think it'll work. All right, so here we go. We know that a sub n is equal to a sub 1, r to the n minus 1, and in this case, n is 3. So the third term, 50, is equal to the first term, 2, times the common ratio, which we don't know, to the n minus 1, or in other words, 3 minus 1, 2. So 25 is equal to r squared, so we can see that the common ratio is 5. And so this geometric sequence can be defined explicitly as a sub n is equal to the first term times 5 to the n minus 1. And so if we wanted to find the fifth term, we would simply take 2 times 5 to the 5 minus 1, or 4. And let's take a moment and actually work that out. So 5 to the 4th times 2. The fifth term in this sequence would be 1,250. So let's take a look at the chess example. Can we find a sub 64, which is the number of grains of rice on the last square of the chessboard? Well, remember, this sequence looked like this. We started with one grain on the first square. Then we doubled it each time, etc., etc., etc. So let's take a look at the recursive definition, or the explicit definition. So we have a sub n is equal to a sub 1 r to the n minus 1. So in this case, a sub 1 is 1 and r is 2. So we're interested in the 64th term. That would be equal to the first term times r, which is 2, to the 64 minus 1, which is 63rd power. So just on that last square in the chessboard, it's such a large number, our calculators write it in scientific notation, 9.22, I'll just estimate it, times 10 to the 18th power, which means take this decimal point and move it to the right 18 places. So you can see that's quite a few grains of rice. But that doesn't even answer the question altogether, how many grains of rice were on the entire board. Because to answer that question, we would want to take the first square and add it to the second square, and add it to the third square, add on the fourth square. So you can see that it's a different process. This addition problem that we just wrote down is called a series, and that's what we're going to learn to do in our next section.